I was hesitating between doing a slides-based talk and a live coding talk. I'm going to do a weird mix of both, I guess, and see how it goes, and you tell me if it works for you, okay? So, let's start with the actual problem we're facing. You have to know that I work with the games people quite a bit. Some of you might already know about that. So they're trying to display pictures very quickly on screen. And sometimes they write things like what you see there, trying to put an image every 60th of a second or something like that. This is bad code, by the way, but we'll return to that. My point is not that, don't worry about it, it's not a display kind of thing. It's about the time that remains when you finish displaying. So this thing is a weird piece of code that's trying to put pictures on screen every 60th of a second, as I said. Simplified, it kind of looks like this if you remove the croft a bit. Now, written like this, it wouldn't give good results because the time to display your images tends to be kind of stable, and the time to prepare your images tends to fluctuate a bit, which means that within your cycle of a 60th of a second, well, you're going to end up with jitter of sorts. Probably better this way. Okay? But some books show it the other way, which doesn't really work well. Now, that's a very simplified picture, of course. People who do that, they're trying to do some kind of real-time system that doesn't kill anyone most of the time. If they're not doing a right job, they're just going to lose money. They're not going to kill anyone, but still. The kinds of problems they're facing tend to be of the four following categories. They're either trying to do something at a constant rate, which is what I'm trying to do now, or sometimes regular, for which the first example would be fitting, I'd say. Or you're trying to finish early or start at a very low latency once something has happened. So I'm going to be concerned about this one right now, trying to maintain a constant rate given some circumstances that we'll come to in a second. Okay? Yeah. Every 1/60th of a second for constant and 60 times per second for regular, which is not exactly the same thing you think about it. Okay? So I'm more interested about constant than regular in this case. So returning to this, it's the sleep that I'm interested in. Okay? So what do we do instead of that? If you read people like Bruce Dawson's blog, who keeps complaining all the time that people sleep too much, and he's totally right about that, people tend to do that. You know, they display stuff, and then there's some remaining time, and since they're trying to achieve a certain rate, well, they're wasting time in the middle, or just they're trying to put more pictures on screen, but sometimes it's just wasteful. You could do something more useful at the same time, or instead. Let's put it this way. So yeah, wasting time is not cool. So what could we do instead of wasting time? That's the plan. The students I work with, when they do this, I'm telling them, don't you have something to do instead of just wasting CPU there? Couldn't you just prepare something for the game you're trying to make that will make the entire experience better instead of just wasting your cycles? We could do many things. Okay? They could prepare resources, decompress stuff, prepare some audio, prefetch assets, or whatever they want to do. If they have nothing to do, of course, they can sleep. Nobody's stopping them. But if they can do something, maybe the overall experience will be better. I don't know about you when you're playing games, but I don't play much games, but when I do, waiting after a game, I hate that. So when I can move through a large landscape without ever stopping, that makes me happier than when I have a waiting screen with something scrolling saying ... or something like that. That bugs me to no end. Sometimes I stop playing because it just breaks my experience personally. I like it when it's fluid. I like it when there's less pauses. So something like that, I'm wondering, why? Why don't we do something useful about that? This is more real code, though. So what could we do there? We can do stuff, but we have a constraint. And that's where the real-time part goes in. The actual real-time thing is displaying your images at a given rate. So the time that you have there, which varies, sometimes it's longer, sometimes it's shorter, you could use that to do something else, but you cannot do something for more than the remaining time because you're going to break your cycle and you want to do a constant rate kind of thing. So you're trying to achieve something interesting, but you have little time. Okay? So the point is try to use this thing. My example would be naive. Okay? You won't do that in the game. It's just for the technique's purpose that I'm doing something simple that I can explain in a group of people within an hour time span at most. So trying to do some auxiliary tasks that but that it will make the experience better if we do something useful, of course, make the system fluid, but not make us break the constant rate we're trying to achieve. So in this simple example, what I'm going to do is do compression of images using RLE compression because it's simple. That's really the goal. Okay? But that's not what you would do in real life. Of course, you do something more interesting than that for your own purposes. If you don't know what RLE is, I'm going to give a very quick overview because that's really not the point. It's just to have something that's easy to make an illustration out of. And I'm going to work with straight 24-bit pixels, RGB, again for simplicity purposes. Okay? There we go. So what are we talking about? If you don't know what it is, most of you probably do, but I don't know. So the thing stands for run length encoding. It's not something you will want to carry back home with you. It's simple stuff. It turns your sequence of values into pairs of how many, what. How many, what. So it's a very simple compression format, but it works well for some kind of pictures, though, or even some kind of other stuff. So if you have something like this, like A, two Bs, a couple of Cs, one D, a couple of Es, F, Gs, after compression, in this case, we would have 3 As, 2 Bs, 5 Cs, 1 D, 3 E, 5 Fs, 2 Gs. And you went from a length of 21 to a length of 14 with this simple example. So kind of okay for this. Okay, there's much better stuff than that, but this is simple enough to fit in the kind of thing I'm doing right now. For this, RLE is awesome. Of course, you don't compress these things quite often, but it's awesome. 5 by 5 stuff, and you end up with 25 red, like, you're happy. If your games look like that, they would be boring, I agree, but it's a very good algorithm for this. I once looked at the zip format, and there's some kind of header that says if they tried some other formats, and it's one of the formats that they try for some pictures because this just works well. For this, it's also a very good algorithm. So if you have a 5 by 5 there, and only your first line is blue, you end up with probably something that's kind of perfect. It's very, very, very cool. Okay. Still okay? You have something like this. It's still okay, but it's okay-ish. Because if you rotated the thing a bit at first, you would get better results. But if you just take it at face value, you end up with something that's reasonable, but not terrible. You just got 20% off of it. It still works, you know, but yeah. And you have a really cool worst case, which is this, for which the compressed format is worse than the original format. So of course, if you have something like this, you won't use RLE. So as you might guess, this is not the proper format for compression of pictures you took on the streets of Toronto this week. It would be awful. But again, if you have kids, I have quite a few, well, you know, those pictures that they make with lots of brown and stuff, really good. So it really works, okay? So, cool for some stuff, but the point, as I hope you understand, is not compression. This is just an example of an algorithm that I'm going to trick into fitting into the time that I have. That's the goal there. To do this, so a few words on the representation of data we're going to take, because if you're trying to compress pixels, well, the first thing you have to wonder is, what's a pixel in my case at the very least, okay? So I'm going to go with something very, very simple, 24-bit RGB. There's many ways to do this, of course, and I'm going to use encapsulation because this way we can play with the representation without changing the client code, which is awesome. So if you don't mind, let's try to have a picture with us. Visual Studio, come to me, please. There we go. So I'm starting with this. What are my options to represent a pixel that will be a 24-bit RGB? What would you use? Suggestions? Hey? 32, yeah, well, 32 bits, okay. What would you use? uint 32? Yeah. Okay, so we have this. uint 32t. RGB, RGBA, say something. That's an option. What else would be possible? You could use an array of just 4 bytes. An array of 4 bytes, cool. So let's do this. So unsigned car. Std array, same thing. It's the same thing for us. RGBA of size 4, std array if you want, but that's going to require an include, and I don't want to do that. What else? Bitset? Why? Something useful. Not string, please. Babysit is cool, but not for this. 4 floats. You're so mean. You got 4 chars could be okay, yeah. So unsigned car, RGBA. Sometimes people will tell me, well, use 3 chars, going to save space, but then you're worrying, well, Mac cache, how will it work? There's many options in there. So there's others. I've heard float for real from the Unity people that they use that for some tricks, but I'm not a graphics expert, so I'm sure they have very good reasons for that. And if you've seen my website, you know I'm not an expert on colors either. I heard some people laugh, you're not nice. Depending on what we do, is going to influence the way we implement our functions. And red, green, blue, of course. I typed this before to save time and see what it gives me. I get what I deserve there. So these will all be trivial to do. What are the other operations we are going to want to implement? Now that's the point, because if we're choosing a representation, some of the things we're going to do are going to be faster, and some of the things we're going to do will be, well, less fast. Maybe not slower, might be a bit too much of a term, but you know, you're going to make trade-offs. If what we're trying to do is achieve something like RGB compression, what will we do? We'll be taking our sequence of pixels, take the first one as a reference point, and try to find the first one that's different from this. And then once we have that, we're going to compute the distance between the first and the last. This will be the number of elements that we have. We're going to say, we have that many of that color. And if we're wise a bit, we're going to end up with 2, I guess, 32-bit integers, because we seem to be targeting 32 bits in this case. So we're going to do 2 things mostly, which is compare with different them and convert to some kind of integral. Which of the 4 would be a better fit? Which of the 3 would be a better fit for this? The first? Yeah. My guess is the first will be more efficient, because comparing integers, equal is going to do a good job for us, and while converting to integers is going to be very quick. Okay, so this would probably be the best representation for what we're trying to achieve in this case. So cool. So let's take this, like this. So, but that means that for the red, green, and blue, if we code them, we're going to have to be doing some bit manipulations or bit masks. Happily enough, for my example, I don't really need them much, so I'm going to put them aside and concentrate on the 2 that we really care about, which will be equals, because we don't need to compute different from anymore with C++20. Const expr, boo, like this, with another pixel of some kind there. Other. And since we picked that representation, this should be pretty nicely done. We're just going to compare the values, which we called this. So regardless of how we map the R, G's, and B's, this will do the job because we're going to be using the same representation on both sides. Is this okay? Making kind of sense? Okay. So we're getting different from for free in this case because C++20 is nice for us. So we have this, yeah? Could we use a spatial operator here? Yeah, we could. If I wanted to implement it, we totally could. We just implement it, yeah.
Or can you just explicitly equals default that?
Well, yeah, it would probably work in this case indeed, yeah, because the representation is very simple. So yeah, we could probably do that and get everything for free. I'm not sure I need spaceship because I don't want to compare things for ordering in this case. So equals probably. Yeah, I know I was more answering Richard's, but yeah, equals default is probably going to do the job in this case too. So we're getting, the point is it's fast and we're getting different from for free. And the convert to uint32 is going to be nice too in this case for obvious reasons. So operator uint32t, like this, const no except blah, blah, blah. Return the value RGBA, something like this, const expert. So we're going to have something that should be pretty efficient for the things that preoccupy us, which is trying to find if they're different and count how many there are, should be okay. So, but these are options. We could do something else, depending on the kind of code we're going to be writing. So if we return to this, if you don't mind, for a second, there we go. So in the slides, there's exploration might be too much of a word, but a few examples of things we could do. So let's just quickly go through them. So something like that would work. Sometimes people want this to say, it's going to be more compact. Maybe. maybe you could see. This is an option. You get an alignment of 1, size of 3. Why not? You could go with this, which we could have done. Sometimes I do this with students because they're convinced it's better, and we just do the bit masking. Why not? Sorry? Why not a what, I'm sorry? A union, you said? And what would be the use? To map the RGBs more easily? Why not? You could do that. So this way you wouldn't have to do bit masking yourself. You just have to be careful in the sense that the order of your bytes will change from machine to machine, so your mapping will not be stable if you do that. So it might be better to mask it yourself, but you decide. You're a free person. If you don't want to communicate with other machines, you might be safe. Cool. Yeah?
I'm just saying there's no safe way to do that without undefined behavior. That's all.
As long as you're within your own machine, you're okay. If you're talking to some other machines, you're on your own.
No, but if you're accessing the non-active member of the union, it's undefined behavior.
But why would you do that, you monster?
Well, but there'd be no reason to use a union. We're going to do that.
Okay, so don't talk to Jason, he's evil. So there we go. Things like that I hear sometimes. People think it's different from an array. It's not in this case. It just does the same thing pretty much. And this is what we're going to use because this is what you picked. So why not? It works. So the main goal when I'm talking to students, the goal is what are we going to use in terms of our algorithms, but you already decided we're going to be comparing stuff with different from and turning into integers, so we're going to be pretty cool there. So we're going to want to implement this algorithm now, and our reflex, because we're C++ programmers and we're very good, is to try to make things quick. So let's see what we can do if my machine gives me back my tools. Please come back. There we go. So let's try to do this thing. Did I have an algorithm? No, I didn't have it. So let's just type it. So we're going to want to do something like, I'm so used to typing template. Please, vector of, I'd say uint32t. It's pretty nice if we have the same representation for our number of elements and our values. Otherwise, we'd be stuck playing with pairs and stuff like that. RLE compression, maybe or something like this, with as input a vector of pixels. My typing is bad today. Something like this. Yeah. Let's call it pix to be original. Okay. So there's many ways to do this, but it's not a complicated algorithm, as you can guess. You can just get rid of the empty vector case at first if you want. That's an easy one. So something like you make your vector in which you're going to put stuff right away empty, whatever. And if there's nothing in your pixel thing, you just return V and you're done. So that's one thing. Or you could just return brace. It's going to do the same thing in this case. And then you pick the first value from the vector because you know there's one now because it's not empty, you just checked it so you're happy. So something like this, I guess. Let's call it base. Something like this. And then you start from position 1 and you go up and you look for something that's different. You could do that with algorithms or something, that's fine. So let's make it simple. For size, I'm going to be lazy, okay? I is less than the size of V, plus I or something like that. So we're looking for something that's different from the base. So let's see. If we found something that's different, base is different from the current element like this. Woohoo! We have the end of a consecutive sequence of similar values. We're very happy. So what are we going to do? We're going to compute the number of elements that we had. So base is not good there because it would be easier to keep an index instead. So it's V of base, something like this. Not pix of base, yeah. And pix of I, this is better. So then we have indices, it's going to be easier to compute stuff. So the number of elements would be a subtraction, I guess. Something like that. So we could push back I minus base, which is going to be something that's larger than 0. I think we can agree on that. And we could push back the value that we just found, which was the value of pix of base in this case. Something like this, which should, if we're lucky, give us an unsigned integral because we have defined the operator for that. Yep.
Sorry?
Isn't it what I'm doing? No, it's my fault indeed. Thank you. I'm so used to typing V that live coding, I get into a mess. You're very sweet. Did I make other mistakes? Yeah, cool. If I make other mistakes, tell me. So now that we've added this, now we found something, we're very happy. We have a new base, which is I, because this is where we found the first thing that is not like what we were looking for, and we continue from that point. Won't we? Are we done? Are we done? Are we missing something? Yep. That's it, which is typical from those algorithms. Once you've gone through everything you could, the last sequence is not taken into account in your vector. So you have to repeat your code a bit, which is not that bad, but it's something like this that you're going to have to do in the end. So it's going to be something like v that's size of pix minus base and something like that. So you should, at this point, have something that kind of looks okay. Richard, do you have a problem with this? It should be pretty much okay. So this probably works. Let's just see if it works. I put some values out of curiosity there. It's complaining about my constructor because I didn't write any. That's a very good reason. Let's add a constructor there. Just make sure the code compiles. A pixel that takes 3 unsigned cars. RGB. Why not? Let's not be scared. And we don't really care about what we're going to do as long as we do something that's coherent within the code. So let's make it simple. RGBA will be made of, let's say, R pushed by like this by 0, and I guess G pushed that way by 8 or something like that. Or I said, and B push that side from 16 or something like this. It should probably do something that makes sense within. Is there anything really wrong there? It's probably okay, as long as it makes sense, okay? So we have a constructor there, and our 2 pixels constructed with the same value should compare equal if everything makes sense. So I put a very interesting thing there. I put I have a couple of greens, a couple of blues, and a couple of reds there, and I tried to write this as X thing that I wanted to make nice earlier, and I said consider take an unsigned integral, and now I'm surprised to see that it doesn't want to accept UN32. Ah, this is interesting. I'm just going to cheat the system for a second, okay? Is it like this now? It doesn't like this. Oh, that's bad. Well, I wanted to display something that's nice. I'll explore this later. It doesn't really matter much. So just put it this way and see if we have the right values at first. So let's try to see if the pixels display right. We're hoping that, so before compression, we should have something. And after compression, we should have something interesting too. I want to do something nice. It doesn't work. So the compression should finish with an even number of values in the vector because I have pairs of how many, what. The assert serves for this purpose in this case. And normally I should, before that, have about 10, 20 values in my vector before compression. Let's hope it works. I didn't try it out, we just typed it. It doesn't work because I'm trying to do things too fast. It's complaining because I'm getting an int and it wants something else. There we go. Complain, I don't mind. So we have similar values at first, and as we can see, I would have liked to display it with hexadecimal values, but we probably have the right things there. There's a number of 255s at the end, a number of big ones in the middle, and about 10 smaller ones at first. These are probably the right values, okay? So after the compression, we seem to be having an hourly thing too, so how many watt, how many watt, how many watt, the code works, okay? Now that this is said, why is this solution not acceptable for our use case? What is wrong if we're trying to make sure we don't exceed some given time there? Yeah?
Well, we can stop the algorithm.
I'm sorry?
We cannot stop the algorithm.
We cannot stop the algorithm, so that's a problem because we would like it not to exceed the time that we have. It doesn't even know how much time we have. Yeah? It's going to allocate memory. That's terrible because allocating is undeterministic in terms of time. This cannot work, even if it's fast. It's not predictable. Cool. So I knew that Timur would say that. Anything else you see? We have other problems. The time it takes to process the input depends on the length of the length of the input. So we don't have any control over what's going on. So now we don't have an algorithm that works for our needs, even though it's probably the fastest it could be or something like that. It's pretty close. It's just not fitting our use case. So sometimes you have the right algorithm, but it doesn't work. It works. But you know what a real-time system is? It's a system that if it doesn't deliver the values on time, it's like if it didn't deliver the values properly at all. It's not useful at this point. If you're braking, you hit the wall and the brakes kick in afterwards, it's not that useful. So we have a problem in this case. We're going to try to fix this thing. Please come back to me. Cool, this is what we have. There. So this is probably pretty much what we just typed. It should be pretty close to, if I'm not mistaken. Yeah, that's pretty much the same thing as what we had in the example we just wrote. So we have something that works. We're taking the inputs we want, getting the outputs that we expect. The signature is straightforward. It's easy to use. You just call it. It returns the right thing. This is awesome. Normally we'd be happy with something like that, you know? And we don't forget at the end to properly put the last sequence in there. This is something people often forget, but since you're experienced, you saw it right away, which is awesome. There we go. And we probably picked the right representation for what we're doing too, which is a good thing. So properly aligned, properly sized and everything. This is cool. The algorithm is trivial, we saw it. But as you saw, even if we optimize it, it's not doing the right thing because pushback, amortized OR1. And in this case, we could be saying, well, I'm going to try to reserve the memory beforehand. But no, it doesn't work because we're still allocating. For one thing, this is bad. And the other thing is, even if we had a very cool allocator, how much would we reserve? Well, we know. We would have to reserve for the worst case all the time. So it would be twice the size of the input. So it's highly aggressive allocation in some cases. But just allocating, unless you pre-allocated the chunk of memory and are using an allocator that's over1, that exists, you can do that, it's going to get tricky. Okay? So this is bad. Yeah, we have this. Reserving, as we said, would take a lot of memory, even if we tried. Even if we reserve, the time it takes to process the input is dependent on the size of the input in this case. We're not stopping anywhere, as your friend said there. There's a number of issues with this, which is kind of a sad thing, but you know, this is what we have. Okay. So to use it in the context that we were targeting, we need to make some modifications, which is the purpose of the talk. So what do? We must, as the first friend said there, make sure it doesn't run for too long. So there has to be a way to tell it stop at some point, or to inform it that it's time to stop, or something like that. There's a collaboration between caller and callee that we have to put into place. We have no choice. There's many ways to do this. You could say you run for that many iterations in the loop and then you stop. That's kind of tricky because you have to know what the loop does. You can give it a deadline or a maximum execution time, like I'm giving you that much time, then you stop. What I personally prefer, that's what I'm going to use, is a continuation predicate. I'm going to pass a function that the algorithm will call and will tell it if it can continue or not. This way, the caller can decide the strategy that suits it best. And you're not as dependent on the way the algorithm is built, presuming that the algorithm calls a predicate from time to time. But if it doesn't, just don't call it. There. If we want to make progress, we're going to have to stop and continue at some point. So that's another thing. Our interface will have to change. It will have to change because right now we're just returning the whole result at the end. But now we're going to have to make progress step by step in some way. So we have to return partial results. Yeah, that's pretty much what we have to do. Unless we make the function we have stateful and turn it into a class, but that's not necessarily a good idea in this case. So we'll have to change the function signature to something that is maybe a bit more complicated. But we need the flexibility to suit the use case we have in mind in this case. Cool. And yeah, well, as Timur said right away, because he's doing that every day, we must ensure we don't allocate in the function, because if we do that, we cannot guarantee anything. That means the caller has to be responsible for allocating the memory. So if you're saying, ooh, that's ugly, you say, well, that's life. You don't have much of a choice in this case. The caller knows when it can allocate. It can pre-allocate a buffer of some kind, of something static, whatever. But if the function has to allocate, the function won't do its job. It's not going to work. So we're stuck. There. So this could be a signature we could try. This is what I'm going to do. There are more arguments, and the return value is different, as you can see. What do I do with this one? So I'm passing it a pair of iterators on the input sequence where I have to begin processing and where I should end. The beginning will advance in between calls. The end will remain stable for a given input in this case, but I'm going to pass it every time just to keep things fresh. I have the output iterator to which I'm going to write. So the destination will move too, because if I'm writing into a pre-allocated buffer, I'm going to, every time I'm called, be a little further in the buffer when I'm writing my stuff. The predicate there is the condition I'm going to test from time to time to make sure I can progress still. And if it tells me no, please stop, then I will gently accept and stop working at this point and return the state of the computation where I am at this very moment, which is the pair that you're getting there, a pair of where I am in the input and where I am in the output, such that the caller can take these and feed them back to me when it's ready to call me at some later point in time with a different predicate, because the time allotted for the computation the next time might be different than one from the current time. So far, so good? Cool. So something like this. The old signature was much simpler. It was much cooler, you know? But again, if we want guarantees, we're going to have to do something about this. Now, this is it. So we have a half-open range, begin, included, and excluded, respecting C++ idioms. If you're saying you should use ranges, no, not there. Maybe I could, but it's not the point. The output there, in my example, you will see I'll be using a back inserter, so the caller will accept allocation, but that doesn't matter to the function that I'm calling. The function I'm calling is providing the guarantees. So if the caller doesn't care, that's the caller's thing. It's just to keep the example simple. And the predicate is the condition, something that I will call, and will return true or false. Now, the caller has no way of knowing when the callee will use that predicate. So ideally, it should be something that's not stateful, because if it's something that is stateful and mutable, at the very least, well, the number of calls you will make might influence the behavior of the algorithm. So something like this is probably not the right thing to do, even though I could do this for test purposes. But no, the more I called it, and the worse it will behave. So this is not something I would wish for, but it would be an example of something I could try just to debug stuff. Is this okay so far? Okay. Are people comfortable with the mutable syntax there? It means the lambda is not const. Okay? Don't abuse these things. I know that Timur knows lambdas a lot too, because he gave a talk on this week. Cool. And again, the pair is because you need two things on output. You need to know where you stop reading and where you stop writing. So you need both to continue your work. So when we start, it's kind of the previous algorithm. If there's nothing left to process, you can just leave. I mean, why work? There's nothing to do. Before, we had a vector that could be empty. In this case, we have a pair of iterators that could be equal in this sense, because either we have completely processed the sequence and the caller has made a mistake, or the sequence was just empty, which is something that happens sometimes. Well, if that happens, there's nothing to do. Okay. The overall algorithm is pretty much the same. What I have inserted in there is an if pred at the beginning. So when I'm iterating, I'm checking my condition, and if my condition says, nope, you cannot continue at this point, well, I'm going to leave it, that's it. And I'm going to leave with the state of things as is right now, trying to make sure that I'm not losing any information, of course. So I'm returning the current reading point that I copied and the current writing point that hasn't changed recently at the very least. And then, if the predicate didn't say, yeah, you should leave, well, then I'm looking for the first element that is different from my base one, and this is essentially the same thing as I was doing before. So if you look at this thing, I'm using the distance to know how many elements I skipped. This thing means that I could sometimes make no progress at all. It is possible. It is possible that I have a long sequence of red, and I'm trying to process it, and I'm cut off before the end, and I've made no progress. This is something I'm accepting. I could do something else. I could say, okay, I'm going to accept a less than good compression result. And say I have 200 reds, I could say, well, I have 120 red, and then 45 red, and then 35 red, which gives a less than ideal compression. But if my principal preoccupation is not to exceed the time I have, and I want to make sure I make progress, I could do something like that. And then post-process maybe the stuff afterwards if I have some time to get a better compression rate, should I be so inclined. Or I could just do what I'm doing there and say, well, sometimes I'm going to be called, and I'm not going to progress, and I accept it. That's a design decision. Is that okay? Sorry for my throat. So this is where we are. This is what I just said. And it's a choice with consequences. If I put the predicate there are consequences to that. I would be making progress every time, but I might sometimes exceed the time that I was allocated, because if I'm on a long sequence, and it takes too much time to find the end of the current subset of elements I'm looking at, well, I might exceed the time that I have. So even though it could give better results and ensure progress, it might not meet the needs of my algorithm. Okay. Is that okay? Cool. There we go. Yeah. And another option, so yeah, that's it. It's like bad quality and stuff. It's kind of like what I just did. I just increment from time to time, and maybe I will exceed the time that I have. There. Of course, you must not forget to take into account the last bit of sequence at the end. But if you're at this point, it's because you've processed everything, and you just had to count the end. So this is constant time stuff, so it's probably okay. Cool? Cool? Cool. There. I left a link in the notes, so if you want to take a look and see how it works, it just works. You have a question, my friend? Richard seems to be preoccupied. Tell me if you find what's preoccupying you.
I'm just trying to determine if the predicate is returning the current base.
The predicate's returning true or false.
The predicate returns false. So in the for loop,
Mm-hmm.
are you incrementing your...
I'm incrementing the base after a subsequence has been found. So I might be making no progress with this implementation. Okay. Is that okay? Cool. Whew. I was scared. So yeah. So if we're using this, looking at the code that we have there, so this is just toy code, of course. I'm putting, this is the same code I was using. I'm putting a number of greens, blues, and reds, or whatever. There. Yeah. The straight and place back would be cool, I know. Before someone tells me, Jason, I know in place back would fit there. So before compression, this is a display that will show the sequence that I have with proper X stuff. I was trying to do something cute earlier, but obviously it didn't work. And I will see the result that I expect. Something like this in this case. Okay. So if I count them, I will see that I have the proper number of reds, greens, and blues, and whatever in the proper order. So there's no surprise there. And the initial algorithm is pretty simple. You call it, you get results. It's an even number. And then, since it's an even number, you can display the elements like 2 by 2. How many watt, how many watt, how many watt. And in this case, if you display the watt in hexadecimal format, it just reads better. Okay, so that's why there's formatting in there. It's from IO-manip, it's old stuff. Print would probably do a better job. Okay. Questions? Trivial? Cool. That's what we have. So it's easy. It works. And this is what we get. It's pretty much what we saw earlier today together. Now, if you're trying to use this thing with the divisible version of the algorithm, well, it's a bit trickier if you look at it. So you end up, at first, I take an iterator to the beginning of my source sequence because it was going to progress from time to time. And in this specific case, I'm using a back inserter to make the example simple, but that's not what I would do in real life. I would have a buffer that's big enough for my needs, whatever it is, and I would progress through that because back inserter does pushbacks, and pushbacks reallocates. But that's besides the point for the algorithm itself. Okay? And if you look at it, until I'm at the end of my stuff, I'm calling and I'm recuperating after the call where I stopped reading and where I stopped writing, and I pursue from that point on the next call. So I will progress slightly. The little dot there that you see, the cout dot with a flush there, is to make sure that I can see that there has been some kind of progress along the way. If you display it, you're gonna end up with something like there. I have an output with small dots that I will show you, but anyway. So once you're at the end, you still have an even number of elements. That's part of the deal because you have pairs, of course, and the display should be similar in this case too. And the small 2 dots, as you see there, is because the lambda I use for my continuation in this case stops after, I think, 12 tries. So I do 2 passes because there were 20 elements. It's just for show, to show that it takes at least 2 passes in there. Making sense? Okay, cool. So again, the goal is to show that we can do this thing more slowly because the first algorithm was better, but within the constraints that we were imposed in the first place. So we can use the time in our real-time loop that was left in between 2 calls to do some useful work in order to make the system more fluid in the end without breaking the constraints that we have, okay? This was the point of this thing. So yeah, the 2 dots are what I said, and you can play with the code if you like. Cool? Cool. So it's a misnomer, because the algorithm indeed, in the end, is slower. And we have to accept it. It does more work. It stops and continues. It's more complicated to use. But the overall system is better because instead of not doing stuff there, and at some point pausing to prepare stuff and making the experience worse, well, you might end up with something that's more fluid because you're not stopping, because you use your time to do something else. So from the perspective of the algorithm itself, you're slower, but the algorithm is not the point. The point is that it's within something else, and that something else is fast. And the overall system gains a bit because of what you did. Now, even if the system is more efficient, you might be wondering, well, this is not modern. Coroutines should be really cool for this. Eh? Yes and no. Yes and no. But yes and no. And Richard, the reflex that you have now, yes, because we're all saying the same thing. The problem is that the continuation predicate has a delay to play with that changes with every call, but it's only passed on the first call to the function. So when you call the function, you pass it arguments, and these arguments contain something that says when you should stop. But every time you call the function, the conditions are not the same because you don't have the same amount of time with every iteration that you're doing because the pictures don't take the same time to prepare. So yes, coroutines work in this case, but you have to be a bit tricky. Okay. I like coroutines too. I'm not saying don't use coroutines. I'm just saying it requires some care. So they are resumable. They're meant to be interrupted and pursued, which explains Richard's happiness a few seconds ago. But you have to be careful. I understand happiness and I'm all for happiness, by the way. So if you're taking something like this, okay, suppose that state is something you're trying to produce, and I'm doing work. So I'm doing my code, I'm in my loop there, and if the predicate says, no, you should stop, I'm yielding the state in this current state. And then I'm doing something that requires a lot of work. It's a sleep, just for a joke. And then I'm checking, should I stop now? If I stop, I yield. And then my state in this case is an integer, so I'm incrementing. So I'm going to loop, and at some point I'm going to stop, Now the pred there, it's only passed the first time I call the function. So if I want this to work in the context where the time that the pred uses to determine whether we should continue or not changes over time, it means that it has to be something that is stateful and holds information that will change over time, like a reference to the current delay that I have in my hands to do the work. If I could pass a new predicate every time, that would be cool, but it wouldn't be a coroutine in this case. Am I making sense? I'm hoping, at least. So something like this, this is kind of a joke, of course. And this is the quote-quote effort. The problem is there. So when I'm going to resume, the predicate will be the same, but the time will be different. There. So this is code that would take that into account. But as you can see, I'm using kind of a nasty lambda to make it work. So I have my deadline initially, that is, I'm giving myself 150 milliseconds or so, and I get a reference to the deadline. So after a call, I recompute the new deadline, and then when I resume the coroutine, the time has changed within the lambda, but it's still the same lambda within the coroutines. So because of that, the next call to pred will take the new value into account. But I wouldn't call that trivial. It's something that requires some thought and some care still. Okay. So if you always have the same time, it might be something different. But in this case, it depends on context. Yeah, my friend.
So why not just, in the body of your function, always call yield? Not bother checking the predicate. Just first thing you do is yield and let the caller determine if you should actually, you just call right away.
Oh, yeah. So you're suggesting you call the function, and the function do one pass and then return? It might not fit our use case because one pass could be too long for us because we're depending on the contents of the input. So we want to make sure that the function we're calling knows when to interrupt itself. Remember, we're trying to compute a sequence of values and compress it. So your suggestion might not fit in this case, even though it would be cool. It always depends on what you're doing. If you're doing 1 unit of work, you don't mind. It doesn't matter at all. Is that making sense, everyone? Yeah? Cool. Thanks for the questions. These are cool. So that reference thing might be bothersome to some people, but in this case, it's probably kind of the best we can do without resorting to global variables or some other kind of shared mechanism that is a bit painful to look at. Cool. And yeah, the thing to remember in this case that even though we seem to be calling the function many times, we're calling it really once, and it's the first call really. The rest is resuming stuff. So pred is created once, and that's it. Cool. And this changes the state inside the lambda in this case. Is that cool? Cool. So this could be tricky. Still, the point of this thing was to, well, let's go back in time. We had this loop that had timing to respect. We had a bit of time at the end that we could have used for something useful should we have such a thing to do. If we don't, we don't. If we want to do something, now we have a varying amount of time to play with. And sometimes we have more, sometimes we have less. We don't want to exceed that time because the critical task is not that, it's the loop in which it's inscribed. Some people will say just do more iterations of the loop, but that might be wasteful if you achieved your goal. Maybe if you did something more useful, the system would be better. But just displaying more pictures at some point, it brings no result. It brings nothing new to the table. If you're trying to do some work that will be useful for your code, in that sense, well, the usual approach is to write a good function and make it do the work. But if you just do that, and there's an unbounded amount of computation to do in there, you're going to make sure that your loop doesn't do its job, and people who do real-time systems will have a heart attack, which you don't wish because you like them, they're nice people. So the way I did things in this case is I tweaked my algorithm to make it so I could pass it a reason to stop or to continue, that the signature would take into account that the bounds in which I'm processing data change over time, and a returning state to the caller such that the caller can feed it back to me when it's ready, in such a way that I can interact properly with it and stop at a proper time, while still trying to make progress, which is a general way to see things, of course, because RLE is just a very tiny dot in the ocean of this. Making kind of sense? That was it. Any questions, comments, or threats?
Hey, thanks for the presentation. Definitely an interesting subject to be able to stop the execution of a function. Somewhere in the middle and pick up from there. Coroutines are a solution for this, but obviously there are some caveats. Would something like a virtual machine be a solution for this as well?
A virtual machine in what sense?
So the idea is to be able to interrupt a function at any point in time, right? So if you have a virtual model for computation, you can just interrupt the execution of that.
Some kind of interrupt or something like that?
Yeah.
Okay, that's interesting. I don't know, it would depend, I guess, on your architecture or something. I was focusing on the algorithm and how you tweak it. I wouldn't try to write a virtual machine on my own to do something like that because that seems a lot of work for the kind of results I'm trying to get. But I'm guessing you can.
Yeah, it was more to not have to modify the original algorithm and actually suspend it at any point.
You have to think about the caller side. So the caller is calling your function, the loop has to continue. So since at your return point, you don't have anything left because you suspended the execution of the function. I don't know how to mesh. You would have to rewrite your color code anyway in this case to take that into account.
Yeah, thank you.
Yeah, please.
Just
Hello.
a little thought there. Like, so while the allocation is the obvious thing that is going to be something that's going to
Kill you.
perturb your performance, there's a whole bunch of secondary effects that could also be a problem here. Caching validation, virtual memory, sort of, you could be like, by running other code there, you've opened yourself up to that. I mean, there is a challenge, which is doing work and just going to sleep, and then letting the OS determine what to do next may still be a viable option. Like, you're like, if there was another thread or a thread pool where it was doing work, halting and just letting it run could maybe be an answer.
Absolutely. Well, you have to measure and know your architecture for that, of course. That's the if you're just playing with the actual algorithm and you have an interaction between color and Kali, that's the limit of the control that I have in this kind of code. If you're saying I have architecture that gives me guarantees when I have a thread pool, it's something different. But the architectures that I have that meet thread pool don't necessarily give me that, sadly enough. My friend. Were you there first?
No,
sorry.
go ahead.
Which one? There, go.
Oh, okay.
I'll be back.
You mentioned that allocating is not acceptable because the time it runs is unpredictable.
Mm-hmm.
But coroutine has to allocate at the point. And I was wondering, when is this allocation done so we can do it at a time that is not critical?
First, it doesn't have to allocate,
well,
but it probably will. We would like to give you control over that. There's discussions on that topic, and they've been going on for some time. There are contexts in which we can avoid allocation. I'm not the expert in this. If Gore was here, could tell you when. Maybe Richard Smith could tell you because he's worked on that, I think. So there are cases where you can actually elide the allocation. We made provisions for that with C++14, believe it or not, by saying that new was not an observable behavior if you had the default new in your code. So we can make sure that we can elide that if we can prove a number of things on your code, which is kind of neat. I don't know if you've seen that thing, but you can do with Goldbolt, you can do a new, and if you're using the default new, and you optimize your code, it just goes away, you just have the values. You can do that, it's kind of fun. I can show you later if you want.
Yeah.
So there are cases where you can actually elide the allocation, but in general, generally speaking, when you're allocating, you take an undeterministic amount of time. So the problem is not that it's not fast, it's that you cannot guarantee it's fast enough. You can, of course, write an allocator of your own that manages that kind of thing. No, it's doable. I give classes on that if you want. But it's kind of fun to do. But again, for the sake of this example, that would have been a bit of overkill.
Thank you.
Sure, sorry. Yeah.
I have a question. So in your loop, what you're doing is if you're done, you say you're going to go to sleep for like however much time you have left.
Well, something I took from a book. Yeah.
Isn't going to sleep, or in fact any interaction with the thread scheduler in itself already something that has non-deterministic execution time?
It's bad, isn't it? So I took that thing from, there's a story to that example. Okay? I have a friend who used to do engines for games like that. And the first example that I had that prepares an image and then displays it is already deterministic in terms of time because preparing an image takes variable amounts of time. So in your cycle, you're regular instead of constant in the terminology that I use because your image doesn't appear at the same point in the cycle. That's already bad in the first place. So what could you do? You could sleep for a little less than the time that you need and then start doing some kind of spinning operation or something like that. There's tricks around this, but again, that was not what I was getting at. You can replace that by any suspension mechanism that you can kind of guarantee, I guess. Okay? So I totally agree with you. I even know that on some platforms, depending on the version, sometimes the times you sleep is at most something, and on other versions, it's at least something, so that's highly painful. I'm totally with you on this.
Thank you.
Thank you.
And thanks for the talk. It was awesome, by the way.
Oh, you're very sweet. Thank you. Anything else? You can complain if you want. No? You laughed, I heard you. Well, if there's nothing else, have a very nice day and a very nice end of conference. Thank you for coming.